recording here. What else are we going to want to be able to draw out? Electron configuration. Orbital box sometimes, yes, sometimes no. A lot of books use orbital box because it shows electron spin as well, but let's go ahead and do the orbital box diagram. What would that look like? I would have a box for 1s, 2 electrons in there, and then the next box would be 2s, 2 electrons, and then a series of 3 boxes that are connected. This would be the 2p, 1, 2, 3, 4, 5 electrons there. And so here we see the core. Here's the valence. Over here we can see the core. Here's the valence shell. It's the orbital box. And then the electron configuration. Let's go ahead and do that. We'll just do the standard. We could do 1s2, 2s, 2p, 5. Good. Or rather than writing 1s2, that's equivalent to helium. It would be helium 2s2, 2p, 5. So here was our core, the valence. That's fluorine. If we go to chlorine, we just add another shell on there. So if we go to chlorine, we've got the 1s, 2 electrons there, and then the 2s, 2 electrons here, and the 3 2p's. This is going to be filled. So the helium shell, neon's filled, and then 3s, 2, and then the 3p with 5. 2, 3, 4, 5. And so these would be our core here. This would be our valence. If we write it out with the electron configuration, we're going to see we're going to have the neon core this time instead of the helium core. And it would be 3s2, 3p, 5. So they're both going to have the same valence shell electron configuration, except, what's the difference? The N. And so N equal 2 versus N equals 3. What's different? N equals 3 is going to be bigger or smaller? Bigger orbitals. Bigger orbitals. And that means chlorine should be a bigger atom or a smaller atom than fluorine. Chlorine's a bigger atom. But they both want to do what? Chlorine and fluorine both want to gain 1 electron. That's it. Which one wants to gain the electron more? Chlorine or fluorine? Yeah, fluorine. Fluorine's the strongest oxidizer. And it has to do with the size. The smaller the size, the more that too, but we haven't gotten to that point yet. The smaller the size, the greater the electrical interaction, or this interaction. So fluorine's going to be more powerful oxidizer than chlorine. And then if we go to iodine, iodine's going to have more shells, right? More core shells. But the valence shell electron configuration is going to be the same. It's going to be ns2 and p5. Except it's going to be 4s2, 4p5. But when we get to iodine, here, actually, bromine, sorry. When we get to bromine here, you see that 3D. This is the 3D10. And these 3D10, what do we consider those as? Core. So it's 4s2. So it's the same. It wants 1 electron that'll complete the valence. The valence electrons, another way way of defining valence electrons. The electrons with the highest N. 4, 4, highest N. Because those are the ones that can be attacked. So this is similar. Well, bromine's going to be a lot bigger. You know, it's got a bigger core. And bigger orbitals with the valence. And iodine should be bigger. And so the most powerful oxidizer should be fluorine, and then chlorine's going to be weaker, bromine's going to be weaker yet, and iodine's going to be the weakest out of that series there. So size is going to have an impact, and we can get an idea about the size based on these orbitals as well. Okay, let's take a look at the oxidant table here. So for example, if we look at sodium and potassium are going to have the same valence shell electron configuration. This is going to be NS1. So sodium's 3s1, potassium's 4s1. Both sodium and potassium want to do what? Do they want to gain 7 electrons or lose 1 electrons? Which one do you think is going to be easier? Lose 1. Lose 1. So if it loses this, then we're left with argon. If this one loses, then we're left with neon. When I say left with neon, it's not the element neon. It's the same number of electrons as neon. So which one's bigger, sodium or potassium? Potassium's bigger. And so what does that mean? Which one's more reactive? The smaller sodium or the bigger potassium? Well, you know, if you're thinking about chlorine and fluorine, well, fluorine's much more reactive because fluorine's smaller and wants the electrons more, right? But we have to think about the chemistry that's happening here because if sodium were attacking something to take its electrons, then sodium would be more reactive. But are they taking electrons or are they losing electrons? They're losing electrons, so it's a different story here. So sodium, yeah, sodium would be more reactive in taking electrons, but since we're losing electrons, which one is easier to take an electron off of? A bigger potassium or a smaller sodium? Bigger potassium is easier to take an electron off of because the electron's in the 4th shell. It's far away. In sodium, the electron's in the 3rd shell. It's much closer to the nucleus. And so the further out that electron gets, the easier it is to strip. And so let's take a look at this here. Well, we'll just look at this one first. Well, I'm going to show a series of reactions here, so we'll take a break now and figure out. We'll start again.